Hello everyone and welcome to our presentation on climate and comfort, where we're going to explore the impact of dynamic facade design on building energy efficiency and occupant comfort. In different geographical locations, comfort needs vary widely, whether it's managing humidity in tropical regions, maximizing insulation in cold climates, or balancing seasonal changes in temperate zones. As climate change continues to influence our built environment, the need for sustainable energy efficiency designs has become increasingly important. Understanding how the local climate impacts both the performance of a building and the comfort of its occupants. The relationship between energy efficiency and climate change is gaining more attention from the architectural and construction sectors. As they are pressing global issues, climate plays a crucial role in the design of building facades. A sustainable building envelope has the potential to manage more than 50% of a building's total energy consumption by combining passive design principles with technological innovations. Recent technological revolution has encouraged designers to integrate climatic considerations with digital tools, enabling the development of dynamic building facades that adapt to factors like sun angles and solar exposure, which vary by location and site conditions. Introduced by William Zuck and Roger Clark, the term kinetic originates from the Greek language and refers to behavior driven by motion, emphasizing its core role in integrating with and adapting to the surrounding environment and context. The facade can alter its form either partially or internally in response to external environmental conditions. This adaptability is not only enhancing the building's performance, but also adds artistic value. Geometric transitions of kinetic facades can be translation panels or louvers, rotation, scaling, and material deformation. The proposed location of the project is in Florence, the capital of Tuscany, located on northern Italy, which experiences hot summers but wet and cold winters. The building will be a ground plus 2 floors commercial office building with a total area of 2,167 meters square. The site analysis for this project was conducted in order to understand the site's physical, environmental, and social characteristics to ensure that the design is functional, sustainable, and contextually appropriate. For the climatic analysis, in order to capture the full range of Florence's seasonal variations, the climatic analysis for this project focused on 3 key months: June, September, and December. The following slides will show the concept development of the building, featuring changes in design through base case, efficient case, and optimized case.
The project zoning diagram ensures all areas in the building are utilized, while taking into consideration the exposure of natural lighting and ventilation. The building is a G+2 where you have reception, restroom, workstations in the ground floor, and more private offices and meeting rooms in the first floor, with access to the roof terrace, and more workstations in the second floor with an executive office. After distributing the internal spaces, we drafted our floor plans that we are going to use in Design Builder. The total area of the building is 890 meters square. For our base case, we selected materials that align with Italy's minimum energy efficiency standards, as outlined in national regulations. These materials ensure compliance with legal requirements for thermal performance, energy saving, and occupant comfort, while keeping construction practical and cost-effective. For our walls, we have selected insert block with expanded polystyrene with a U value of 0.33. For the roof, we have selected a flat slab with 100 millimeters of expanded polystyrene insulation with a U value of 0.25. For the glazing, we have chosen double glass with 15 millimeter air cavity, achieving 1.73 U value. While the selected materials in the base case ensures compliance, they are primarily focused on meeting regulatory thresholds rather than optimizing performance. For our efficient case, we upgraded the materials to elevate the building energy efficiency, environmental sustainability, and indoor comfort, aiming to achieve Casa Clima certification, which emphasizes advanced performance and sustainable building practices. For our walls, we have upgraded the selection to air-rated concrete block with glass wool insert and additional mineral fiber wool insulation with stone cladding, achieving 0.128 U value. For the roof, flat slab with 200 mm glass wool insulation, achieving 0.125 for the U value. In the glazing, the selection is triple glass 16 mm with argon, 0.64 is achieved for the U value. We conducted energy performance simulations for the base case of our office building using Design Builder. The results revealed an annual energy consumption of 164.93 kilowatt-hour per meter square with natural ventilation, and slightly higher value of 166.6 kilowatt-hour per meter square when relying solely on mechanical ventilation. To further understand the building's interaction with its environment, we performed a CFD analysis. This provided data on wind, velocity, and pressure distribution across the building facade, helping us understand how to optimize natural ventilation and orientation of the building. We conducted daylighting analysis for the office building across the three key seasons, summer, winter, and fall, at different times of the day, 9 a.m., 12 p.m., and 5 p.m. The results showed a fairly consistent daylighting distribution throughout the year, with the exception of winter, where the sun sets before 5 p.m., indicating that artificial lighting will need to compensate during working hours, particularly in deeper areas of the building where daylight penetration is naturally limited. As mentioned earlier, we have followed Casa Clima energy standards for the efficient case, which is Italy's local sustainability assessment method. Accordingly, we have selected the materials as well as some sustainable strategies, like building orientation. According to our climate study, Florence, Italy experiences winds from the west and southwest during the winter, while warm breeze from the south and southeast are common in the summer. Additionally, passive solar gain and thermal comfort by integrating photovoltaic glass facade, which are solar modules integrated into each glass panel. In our simulation of the efficient case, the building achieved an annual energy consumption of 122.15 kilowatt-hour per meter square with natural ventilation and 122.67 kilowatt-hour per meter square without ventilation. This represents a significant improvement over the base case due to the integration of enhanced materials and systems aimed at optimizing thermal performance and reducing energy demand. Comparing the results with the base case under natural ventilation, the base case recorded an annual energy consumption of 164.93 kilowatt-hour per meter square, while the efficient case achieved 122.15 kilowatt-hour per meter square. This remarks an improvement of approximately 42.78 kilowatt-hour per meter square, translating a 20% reduction in energy demand in the efficient case. Similar to the base case daylighting results, the efficient case daylighting is consistent throughout the seasons of the year. However, since the building has been reoriented, the offices that were towards the north in the base case are now having a better exposure to natural lighting.
The proposed facade design is inspired by Renaissance architecture, which was originated in Italy in the early 15th century in Florence. The inspiration is particularly from the Renaissance rose windows in Florence cathedrals. In Renaissance architecture, circles often symbolize infinity, unity, and the divine. The use of circular shapes serves as a modern reinterpretation of symbolism, celebrating Florence's architectural heritage while embodying timeless themes. For the mechanism, the facade will follow a vertical rotation mechanism, where the facade elements will be rotating around a vertical axis to control environmental factors such as daylight, ventilation, and shading, adjusting in response to sunlight or user preferences. Each panel is mounted on a pivot, allowing it to rotate around its vertical axis. The pivot will be placed in the center of each panel and fixed to the building structure, providing stability to the rotating panels. Each panel will be rotated between 0 and 180 degrees. Rose windows are known for their play with light, filtering it into the cathedral's interior. Similarly, The circular facade could allow controlled light to enter through adjustable openings, casting shadows that mimic the intricate patterns of stained glass. The regular arrangement of circular elements also reflect the rhythm and symmetry seen in Renaissance design, where geometry and order were highly valued. Such kinetic facades depend on the use of lightweight and thin panels. Therefore, organic photovoltaics from manufacturer Armor Asaka will be installed into the glass cells. Asaka's OPV technology is particularly well suited for kinetic facades, as these cells are light-weighted with less than 1 mm thickness, flexible, enabling them to adapt to curved surfaces without compressing performance, and can be designed in custom shapes and colors. These films are available in various colors, allowing for extensive customization to meet design needs. They also perform well under low light conditions, making them ideal for dynamic architectural applications.
We have conducted a simulation with the optimized case that implements the kinetic facade. The first simulation with the 0-degree rotation resulting in 113.67 kilowatt-hour per meter square, and the 45-degree rotation resulting in 111.3 kilowatt-hour per meter square. In comparison with the base case, 53.63 kilowatt-hour per meter square is saved, which is around 32.5%. Adding the kinetic facade enhanced the daylight factor throughout the building. We have chosen one office to compare the daylight factor resulting from the base case and optimized case. The highest recorded daylighting factor recorded in the base case is 29.7 at 9 a.m. on June 21st. Compared to that, the highest daylighting factor recorded in the optimized case is 6.1 at the same time, achieving consistent glare-free illumination that supports visual comfort. By simulating the building with the implementation of the chosen renewable energy, which is the building integrated photovoltaic glass facade, the total energy result is 110.67 kilowatt-hour per meter square. In comparison with the base case, a total of 54.33 kilowatt-hour per meter square of energy is saved, which is nearly 33% yearly.